Now, let's move on to the part of this topic on indicators and pH scale. So, how do we know whether a substance is an acid or an alkali? We can make use of litmus paper, correct? So, litmus paper, the red litmus paper will turn blue if there is in the presence of an alkali. The blue litmus paper will turn red if there is an acid. We can also make use of some substances which we call indicators, which will give us a visual indication of whether the substance is an alkali or an acid. So, for example, the first one is phenolphthalein. It turns pink in alkalis. Methyl orange is the one which we most commonly use in the lab. This one is the most common in the lab. It is red in acids. It is yellow in alkalis. Litmus, as we mentioned earlier, is red in acid and it is blue in alkalis. So what does the indicator actually measure? It measures the pH of an acid. So what is the pH of the acid or base? So the pH is actually a measure of the acidity of an acid or the basicity of an alkali. So this is only measured when the substance is dissolved in water. So to go into a little bit more depth on what is pH, pH is actually a negative log of the concentration of H plus in the solution. So if I have a higher concentration of H plus, I will have a lower pH. So that's why if I have a strong acid which is fully dissociated, I will have a low pH. If I have a weak acid which is not fully dissociated, my con of H plus will be much lower. So much lower con H plus, it means that when I negative log a smaller number, I will have a large pH. Try to sub in certain values. Maybe try to sub in con of 1 versus a con of 0.01, and you will be able to see for yourself why a strong acid which is fully dissociated will have a much lower pH than a weak acid that is not fully dissociated, okay, in the presence of water. So for bases, it is simply 14 minus the pH, and we get a value for the bases. So for acids, they have more H plus and OH minus. For alkalis, they have more OH minus than H plus, and when it is neutral, they cancel out. So take particular note that in an acid there is still OH minus. It is just that the con of H plus outweighs that of the OH minus. Similarly, in alkalis, there is still H plus, but the con of OH minus outweighs that of the H plus. In neutral, it is the same, equal. So this is a table which shows the color changes of some of the indicators. So let's take a look for, say, screen methyl orange. In acids, it is red. In alkalines, it is yellow. But take note, the color changes only at 3.7. So if it changes yellow, it may not truly be a acid. It could be pH 4. Because at pH 4, it will be yellow already. Correct? So how do we ensure that when we add methyl orange, we know that that solution is indeed an alkali? We can always use a combination of indicators. So for example, we can use, if we test a solution with methyl orange and it gives us yellow, we can deduce that the pH will be above 3.7, but we cannot deduce that the substance is an alkali. What we can do is now to use, say, litmus, and we get a blue solution, and then we can conclude it is above pH 7. Okay? But if when I use litmus, I get a red color solution. Okay, so this solution X in methyl orange, it is yellow. In litmus, it is red. It tells us that because it is yellow, it must be pH more than 3.7. Correct? The pH must be more than 3.7. Okay, the pH must be more than 3.7, must be above 3.7. And because it is red in litmus, the pH must be less than 7. Correct? So if this solution X gives me a red colored litmus and a yellow colored metal orange, I will know that the pH for this solution X will be between 3.7 and 7. Correct? Yep. So to narrow this down further, let's say I use screen metal orange and the solution still remains red. It tells me that the pH is between 3.7 and 4. But you notice, right, when I use a mixture of indicators here to tell me the pH of the solution, it's actually not a very precise value which I obtain. It's always a range between whatever and between whatever. So how do we actually get a more accurate indication of the pH of a solution? There are two ways. The first way is still not very accurate, which is to use universal indicator. It gives us a range of colors from red to purple. Universal indicator is actually a mixture of different indicators. It's a mixture of indicators. So based on what is the pH of the solution, it gives us a color. Okay, but this is also not very accurate, because if it is blue, it can be 10, it can be 10.5, it can be 11, it can be 11.1. So it is not very accurate. The most accurate indication actually is given to us by something which we call the pH meter. So a pH meter is an electronic device which measures the concentration of H plus ions based on the measurement of the conductivity of the solution. So we can see what is the conductivity of the solution, and we will be able to determine what is the pH of the solution. So let's say this solution here, the pH meter here shows 7.00, so we can say that this solution is neutral. Okay. Alright, so this is a example of a range of pHs which we can find in nature. In foods, for example, most pickled foods are acidic because the pickling involves the use of ethanoic acid, and ethanoic acid, when it is mixed with water, a low count of ethanoic acid in water is actually called vinegar. So all these are vinegary foods. They are pickled, and the acid helps prevent the growth of harmful bacteria and mold. So these foods can be stored for a much longer period of time. In our human body, the pH changes from our mouth all the way down into our stomach. Our stomach is acidic. Our intestines are, small intestines is actually a bit alkali. So you notice the pH changes as the food moves through our body. Okay? So why are the different parts of our stomach having different pHs? It is because the enzymes in these two areas, in these two areas have optimum pH values have different optimum pH values. So for the enzymes in the stomach, they work better when it is acidic. For the enzymes in the small intestines, they work better when it is alkali. You can read up more about this in the human digestive system or the alimentary canal topic. Alimentary canal topic in biology. Plant growth is also affected by pH values. So in this table here, which is shown here, you notice there are 4 pH values for 4 different types of soil. So depending on what plant you are growing, you will need to calibrate the pH of the soil to allow the plant to grow best. So let's say, for example, maybe tomatoes. Let's say tomatoes grow well in pH 6 soil, and your soil is a pH 8. So you need to bring down the pH to 6. So what do? You add in some acids. Okay, so but at the same time, if your soil is too acidic and your plant requires a more basic condition to grow, you can remove the acid in the soil by adding in bases such as calcium oxide or alkali such as calcium hydroxide. So this is a metal oxide. A metal oxide is a base. If it is soluble in water, it is an alkali. So the presence of these two, they can help remove the H plus ions in solution. They can remove the H plus ions from the soil, and it will raise the pH of the soil. So if our soil is too alkaline, we can add in ammonium sulfate. Ammonium sulfate is acidic. Where is the H plus from? Ammonium sulfate, when it is dissolved in water in the soil, it dissociates to give us NH4 plus and SO4 2 minus. And the NH4 plus here can partially dissociate to give us NH3 and H plus. So this is the source of H plus. So this H plus can react with the excess OH minus in the soil, and it will lower the pH to a suitable pH. This is an example of shampoo and conditioner. So why is a shampoo and conditioner here? I will not review too much here. Why not you ask your chemistry teacher, or you go to the pharmacy to buy some litmus paper and you test the pH values of test the pH of the shampoo and the conditioner. You will find that one is acidic and one is alkaline. So which one is acidic and which one is alkaline, and why is one of them acidic and why is it one of them alkaline? After you test with a pH paper, read up on the structure of hair, and you may be surprised by what you find. You notice that there'll be this term which they use called scales. How can there be scales on your hair? Read up more to find out. So I shall not divulge too much of this mystery. Okay, so now let's move on to a reaction which we actually mentioned earlier, neutralization. So the neutralization reaction, as we went through earlier, is the reaction between an acid and an alkali to form only salt and water. Only salt and water. So why is it important that I cover this thing here? Because later on, when we talk about the oxides reaction, the amphoteric oxides, the acidic oxides, and the basic oxides, you will need to know what is the ion which actually reacts. And when we move on to the last part of this topic on ionic equations, you will need to know as well what is the ions that are actually involved in the chemical reaction. So quick recap first, just do a quick recap here. Neutralization is acid and alkali giving us salt and water only, and this is the equation for neutralization. H plus and OH minus gives us H2O. This is the ionic equation. Later on, we will cover a little bit more on how to derive this ionic equation from the original chemical equation here. I have here on screen three classes of oxides. This is actually not something which is brand new. I have already plucked out some of this from the earlier sections. So acidic oxides are mainly the metal oxides. Basic oxides are the non-metal oxides. So the only one which is new here, which we need to introduce before we begin the writing of ionic equations, is amphoteric oxides. So what are amphoteric oxides? Let's understand a little bit more first on the first two oxides, acidic oxides and the basic oxides. So an acidic oxide is an oxide of a non-metal. For example, carbon dioxide. This is a non-metal oxide. The oxide portion is here. This is the non-metal portion. So a non-metal oxide is an acidic oxide. Okay, and if they dissolve in water, they will form acid. So for example, CO2 is a non-metal oxide. So this is an acidic oxide. It can dissolve in water to give us carbonic acid. Sulfur trioxide here dissolves in water to give us sulfuric acid. This is a component of acid rain. SiO2 here, this is a non-metal oxide again, but it is not soluble in water to give us an acid. However, because this is an acidic oxide, based on the chemical reactions it can undergo, it can still take place in a acid-base reaction to give us salt and water. Later on, we will take a closer look at this. Okay, so acidic oxides react with alkalis to give us salt and water. So notice this is similar to the equation we call neutralization, where acid and base gives us salt and water only. Okay, only. Basic oxides, we covered this quite extensively earlier, are oxides of metals, and those which are soluble are known as alkalis. So common oxides and common alkalis. Similar to acidic oxides, basic oxides can react with acids to give us salt and water only. So recall, this is neutralization, and we have salt and water only. Okay, salt and water only. Which now brings me to amphoteric oxides. Amphoteric oxides. So these are metallic oxides which can behave either as an acid or either as a base, depending on what is the other reactant. Okay, depends on what is the other reactant. There are three main amphoteric oxides which you need to know: zinc oxide, lead oxide, aluminum oxide. So let's take a look at the equations here. So why is it amphoteric? So when zinc oxide encounters an acid, okay, when it encounters an acid, it reacts in a neutralization form of reaction to give us the salt and water. So let's say this is HCl, the salt will be ZnCl2. So this is an acid-base reaction. So if this is HCl, zinc oxide behaves as a base. But if I were to switch the H plus out for KOH, I now have a base and a acidic oxide reaction to give me a salt and water. Okay, so depending on what is the other reactant, amphoteric oxides can behave either as an acidic oxide or a basic oxide. Okay, so with acid, this is a basic oxide. With a base, this is a acidic oxide. So these are called amphoteric oxides. So let's quickly attempt checkpoint 6. Some simple chemical equations here. So pause the video now to attempt this checkpoint. Continue the video once you are done. Alright, for checkpoint 6, the first one is a very simple equation: aluminum oxide with dilute hydrochloric acid. So aluminum oxide, if you recall, is an amphoteric oxide. Amphoteric oxide. So this would be a acid, and because this is acid, it will now behave like a basic oxide. And this is the chemical equation. So acid here, and this is the amphoteric oxide, which now behaves like a basic oxide. Next one, for sulfur trioxide with water. So this is an acidic oxide, and because it is soluble in water, it gives us an acid, dilute sulfuric acid. The last equation is for phosphorus 5 oxide with water. Again, phosphorus 5 oxide or P2O5 is soluble in water. So when it dissolves in water, it gives us the acid, and the acid in this case is phosphoric acid or H3PO4. So other than the acidic oxides, basic oxides, and amphoteric oxides, there is still one more class of oxides which is pretty boring, and we call this the neutral oxides. So they are non-metallic oxides that do not exhibit either acidic or basic properties. Hence, they are called neutral oxides. So water is a neutral oxide. Carbon monoxide, nitrogen monoxide. Carbon monoxide is a neutral oxide because it is insoluble in water as well. So when it can't dissolve in water, there will be no H plus, no OH minus. It can't behave like an acid. It can't behave like a base. So it is classified as a neutral oxide. Okay, so this is the last part of this topic on writing of ionic equations. We have covered all the equations of all the acids with all the different substances, of the bases with all the different substances, and now it has led us to this area on writing of ionic equations. It is very, very important that before we begin with this section, that you know what every single reaction that acids can undergo and every single reactions that base can undergo are. It is very, very important, because without knowing the first chemical equation, okay, without knowing the main chemical equation, there's no way that you can write the ionic equation, because you need to know how to split the main equation first. But once you know that, actually the writing of ionic equations is actually very, very simple. So let me bring you through this in a very stepwise manner. So step one, let's say we are doing the reaction between aqueous sodium hydroxide and dilute hydrochloric acid. So let me blank the screen. NaOH plus HCl gives us NaCl plus H2O. So step one, write the chemical equation. Step one, write the balanced equation. Okay, step 2. Because this is an ionic equation, we must first split this main equation here into the ion components. So NaOH in aqueous state, NaOH in aqueous state, it means that it can dissociate to give me Na plus Aq plus OH minus Aq, HCl Aq, HCl Aq, this is the acid in water, it can dissociate to give me H plus Aq plus Cl minus Aq. NaClAq. NaCl is an ionic compound. An ionic compound, when dissolved in water, can dissociate to give me the ions. So I have Na plus Aq, Cl minus Aq, and I have water here, H2O liquid. So H2O is a molecule. It cannot dissociate to give me H plus or OH minus or anything else. So it remains as H2O liquid. So step 2 is to dissociate into ions. And step 3 is to cancel out the like ions on both sides of the equation. So if we take a look here, what are the like ions we have? Let me change the color of the ink first. We have Na plus and Na plus being the like ions on both sides. So we can cancel these two out. We have Cl minus and Cl minus being the like ions on both sides, so we can cancel this out. And we are left with just these two ions here and water. So for step 4, we rewrite the equation with the ions that are left behind. So what do I have? I have OH minus Aq plus H plus Aq, giving me H2O liquid. And voila, this is the ionic equation. Simple, right? So let's run through this again. Step 1, write the chemical equation. Step 1, write the chemical equation. Step 2, ionize all the aqueous species. Everything which can be dissolved in water can be ionized. So if I have, let's say, if I have NaOH, I can get my Na plus and OH minus. So we need to know what ions, what compounds are soluble in water. Okay, so we ionize them, ionize everything out. Solids, liquids, and gases, we simply write the same compound down. So this is a liquid, we write the same thing down. Step 3, we cancel like ions on both sides. Na plus, cancel, Na plus, cancel, Cl minus, cancel, Cl minus, cancel. And step 4, we copy down whatever is left behind, and we have our ionic equation. Take note, state symbols must always be included because ions cannot exist without a state. Okay, they cannot exist without a state, and they are most stable in aqueous state. So make sure you write the state symbols down. Right. So this is a very simple solubility table which you will need to know. There's more of this. This table is repeated again in the topic of preparation of salts. So from here you notice that all the sodium, potassium, and ammonium based compounds are soluble in water. They are soluble in water. So if I have NaCl soluble, if I have Na2SO4 soluble, if I have Na2CO3 soluble, so long as there's Na plus, it will be soluble. All nitrates are soluble. So if I have NaNO3 soluble, if I have CaNO3, it is also soluble. Chlorides are all soluble except these two, silver chloride and lead 2 chloride. So this is actually a white precipitate. This is also a white precipitate. Sulfates are all soluble except these 3. Carbonates all except this. So if you notice, this is actually the same as this. This is the same. Because so long as you have Na plus, K plus ammonium present, you will be soluble. And lead 2 compounds all are insoluble except lead 2 nitrate. Because nitrate here, again it is from here. If you have a nitrate present, you will be soluble. Now let's move on to checkpoint 7. Pause the video now to attempt the checkpoint. Continue with the video once you are done. Checkpoint 7 is a very good checkpoint because it allows you to write ionic equations out many times. And the only way to improve in writing ionic equations is to practice and practice and practice. There are, let me see, there are 6 questions in checkpoint 7 to allow you to practice on your ionic equations. So checkpoint 7 gives us 6 practice questions. The first one is magnesium with dilute hydrochloric acid. Okay, so step 1, we write the chemical equation out first. So we know it is Mg give me a moment. So we have Mg solid plus HCl equals giving me MgCl2 equals plus H2 gas. So which one can we dissociate? We cannot dissociate Mg, it remains the same. H plus, we have 2H plus, we have Cl minus, 2 Cl minus because the 2 belongs to both of them. We have Mg2 plus here, and we have 2 Cl minus because it's Cl2, there's 2 of the Cl minus, and we have H2. So now we cancel the like ions on both sides. We cancel this, and what is left is just Mg solid plus 2H plus Aq, giving us Mg2 plus Aq plus H2 gas. So this is the ionic equation for part A. Let's go on to part B. So for part B, what do we have here? Part B, we have sodium carbonate in the aqueous state reacting with dilute HCl, aqueous as well. So this is an acid carbonate reaction. It will give us salt plus water plus carbon dioxide. So let's fill in the state symbols now. And we need to balance the equation. There's 2 here, 2 here. So next step, we split the ions out. So we have 2 Na plus, we have 1 CO3 2 minus, we have 2H plus, we have 2 Cl minus, we have 2 Na plus, we have 2 Cl minus, we have water, and we have carbon dioxide. So cancelling for like ions on both sides. Again, what do we have left at the end of the day? We simply have our carbonate ion, aqueous state, plus 2H plus, aqueous state, giving us H2O, liquid state, plus CO2, gaseous state. So the ionic equation over here, notice that it actually tells us what are the ions, or what are the elements, or which species is actually involved in the chemical reaction. So for the first one, acid metal reaction, the metal is reacting only with the H plus. The Cl minus is not doing anything, and we call Cl minus the spectator ion. Call it the spectator ion. So it is just watching only. That's why spectator. Okay. So for the acid carbonate reaction, only the carbonate and the acid portion H plus is involved in the reaction to give us water and carbon dioxide. The rest of the ions are again spectator ions. Let's move on to the next part. Aqueous calcium hydroxide with dilute sulfuric acid. So we have with us here CaOH2 aqueous with H2SO4 aqueous. So this is an acid hydroxide reaction, acid alkali reaction. This is a soluble hydroxide soluble in water. So this is alkali. So acid alkali reaction gives us salt and water. Salt and water. So if we split now into ions, we have these ions, and next step is to cancel out like ions. We cancel this, we cancel the sulfate, What we have left is simply this equation here. Okay, this very simple equation here, which is 2OH minus AQ plus 2H plus AQ, giving us 2H2O liquid. So we balance it. It's 2, 2, 2. We cancel out. So we have left with OH minus AQ plus H plus AQ, giving us H 2O liquid. So this is in fact a neutralization reaction. Okay, so this is in fact a neutralization reaction. This is an acid-base reaction to give us salt and water only. So this is a neutralization reaction. Part D. Solid copper 2 oxide and dilute sulfuric acid. So we have solid copper 2 oxide now with dilute sulfuric acid. What do we have? We have a acid and a metal oxide reaction. So it will get us our salt and water as well. Salt and water, make sure equation is balanced. And now let's try to split this into ions. This is the solid, so it remains. This is the acid. This is the salt. And this is water. Do we have any like ions to cancel over each side? Yes, no, we have only our sulfate ions here. And that's it. So if we write this down again, we have CuO, solid, plus 2H plus aqueous, giving us copper 2 plus aqueous, and water liquid. So this is the ion equation for the acid and metal oxide reaction. Part E, we have aqueous copper 2 sulfate. Aqueous copper 2 sulfate reacting with aqueous sodium hydroxide to give us copper 2 hydroxide, which is insoluble in water. So this is an acid, this is a base, this is a alkali reacting with copper sulfate here. This is not a acid, not a base, but we know that copper 2 hydroxide, which is formed, is not soluble in water. So based on this equation here, what is left? We have Cu out, we have OH minus out. How do we make sure that the left and right side are balanced? We must ensure Na here and SO4 here come together to give us a compound. So we have Na2SO4 aqueous. Right? So next step, split into ions, Cu2 plus, SO4 2 minus, Na plus, OH minus. CuOH stays by itself because this is a solid, it cannot dissociate. It is insoluble in water. And we have Na plus here, and we have SO4 2 minus here. So we cancel like ions on both sides. SO4 is gone, Na plus is gone, and what do we have left? We have Cu2 plus Aq plus OH minus Aq giving us CuOH2 solid. So this is also known as a precipitation reaction. A precipitation reaction. The precipitate in this case is copper 2 hydroxide, blue in color. The last equation here is a reaction between zinc, which is obviously a metal, so it's solid, with aqueous copper 2 sulfate. So this is a reaction which you will learn later on to be known as a displacement reaction. So zinc can displace copper from copper 2 sulfate because zinc is more reactive than copper. But for this question, it has already given you the products of the reaction. From the solubility table, you know that zinc sulfate is soluble in water. So we have this. Now we split into ions again. And we cancel like ions on both sides. And we get zinc solid plus Cu2 plus aqueous, giving me zinc 2 plus aqueous and copper solid. Alright, so we have practiced 6 ionic equations here. If you need more practice, you can refer to the tutorials. If you need clarification in any of the earlier sections, please scan through the video again. We have come to the end of acid, bases, oxides, and ionic equations, so I will see you in the next lecture series. Thank you and have a nice day. Bye bye.